Okay. Okay, great. So this talk, I'll try to cover two papers that we've had in the past years, data-dependent hashing via nonlinear spectral gaps and polar homeomorphisms and approximate nearest neighbors. This is joint work with Alex Andoni, Assaf Naor, Alexander Nikolov, and Ilya Razenshteyn. Okay, and if there's any questions, please stop me and ask. So, okay, I'll first set up the main algorithmic problem we'll be solving, and this is the approximate near neighbor problem, and I'll abbreviate this as ANN. And this problem is a data structure problem that takes place in some metric space. So for us, we'll focus on norms. So the problem is as follows. We'll receive a data set P, and this will be some subset of RD of n points. So think about some points like these. And you want to look at these points and arrange them into some data structure so that in the future you can support the following kinds of near neighbor queries. So a new point Q will come in. This will be some point in RD. And it's promised that there exists a point from your data set within distance 1. And now your data structure should output any point within distance at most c from the query point. Okay? So in this particular case, the data structure can return either p or p prime. Okay, so is the problem definition clear? Good. And when we design data structures, we want to think about optimizing the approximation, this parameter c, to be as close to 1 as possible while minimizing the space that we use and being able to answer query time, having sublinear query time, so not having to scan the entire data set. And you should think about all this taking place in the high dimensional regime. And basically all this means is that when we design data structures, we want the dependence on the dimension of the vector space to be at most polynomial. Good, so let me give you an example of an ideal theorem that we would like to prove. So ideally, we would say the following, that for some norm space over Rd given by x and some constant epsilon greater than 0, there exists a data structure for ANN over this particular norm with approximation which gets order 1 over epsilon, so some constant, when epsilon is a constant, using space which is polynomial d times n to the 1 plus epsilon, and query time which is polynomial d times n to the epsilon. So in epsilon, think about this as being like 0.1, and this means that we can get highly sublinear query time by only giving up a little polynomial amount in the space and being polynomial in the dimension. Okay? So ideally, we would get to this ideal theorem. This would be a constant approximation.
So you're imagining the dimension is, you have many more points than d, and it's much larger than d?
No, so first so n is much, much larger than d, but we still want, d is not too small. So we don't want to be, you can think about the case where d is log n to some small power. Mm-hmm. Yep. Okay. So this work has really received a lot of focus in the past 20 years. And most of the focus has really been designing on data structures where the underlying distance is measured by the L1 and L2 norms. And the main sort of technique, the way to summarize this, is this notion of randomized space partitions. And if you've heard of locality-sensitive hashing, LSH, basically these are all methods to take your metric space and apply some random partitions, and then you look at the parts and you design a hash function which simply maps a point to the part it belongs to. Okay, so for the case of L1 and L2, this problem is pretty well understood, and we can actually achieve the ideal scenario. So already in 1998, this paper by Indik and Matwani and Kushilevi, Sosrovsky, and Rabani, they basically get the ideal scenario for the case of L1 and L2. They can show that for any fixed epsilon greater than 0, they can design a data structure which gets approximation order 1 over epsilon. So constant approximation using space d times n to 1 plus epsilon and query time d times n to the epsilon. Okay. And this work is really trying to go beyond L1 and L2 and try to get a more general understanding of this problem. So the high-level question here will always be what's the particular geometric property that we're going to need from a norm space that will allow us to design efficient ANN data structures. Okay? And just as a quick recap, when I talk about general norm space, I'll just mean, so I want to think about some function which intuitively measures my distance away from 0. So it should satisfy these 3 axioms. But a general norm space will just be general function of this form. And sort of there's a natural correspondence between a norm space and its unit ball, and will be symmetric convex bodies. And the idea is that for any norm space, I can think of all the vectors with norm at most 1, and that will be my unit ball. And likewise, for any symmetric convex body, I can scale it up to measure distance to a point. So like the norm of a particular point is given by how much you need to scale this body so that the point lies on the surface. So let me just show you some pictures. I'll give you an example. So maybe like the Euclidean L2 norm, you measure like sum of squares of the coefficient, then taking the square root. Then the unit ball is just the usual ball that we think about. But maybe we can think about sort of the Manhattan norm, the L1 ball, measure the sum of the absolute values of the coefficients. And now when I say general norm, like really you can expect arbitrary symmetric convex bodies. So maybe something like this or something like that. Or like that, but the idea is, okay, what's the property of a particular convex body that allows the corresponding nearest neighbor problem to have efficient data structures?
What does symmetric mean here?
Right, symmetric means that if x is in the body, then minus x is in the body. So it's symmetric around the origin. Yeah. Okay, good. So maybe let me give you like a first approach to try to answer this question for general norms. Then the idea is this like so-called embeddings approach. So it's like quite natural idea. Want to design a reduction between these geometric problems from some space that I know nothing about to some space that I do know. So the idea is you want to design a function f that will allow me to map points in x to points in y, where y is like a nice space. So think of y as being like L1 and L2. And we want this function to satisfy that pairwise distances between points in x is roughly equivalent to pairwise distances of points in y after I apply the function to each point. Okay? And if this like roughly equals is nice enough, then there's like very natural way to design algorithms for these problems. In particular, if I have to solve the problem in x, I'll first map all my points using f from x to y. And since y is nice, maybe like L1 and L2, then I'll solve the problem in the space y. Okay? And then I can solve for the problem in x. Okay, is that clear? Good, so now that we have this approach, we can sort of look in our toolbox and see, okay, what's the best thing we can do for embedding general norms into L2? We can already use some like very nice theorems. In particular, in 1948, we have this theorem of Fritz-John, which basically says that if you take any norm space x, there exists an invertible linear map, and think about this as being my embedding, such that for any two pairs of points, the distance between x and y in my original space is up to factor square root d, the distance of the points tx minus ty. Okay, so basically, John's theorem is saying that up to factor square root d, an arbitrary norm looks like L2, looks like Euclidean norm. Okay, or we can look at what's happening here in the world of convex bodies, and we can say that if you take any origin symmetric convex body, so think about k as being the unit ball of the norm x, then there exists an ellipsoid E, so it's like a linear transformation of the L2 ball, such that the ellipsoid is contained in k, and square root d times that ellipsoid contains the convex body. So the picture you should have in mind is the following. So we start with an arbitrary norm, and now you can wrap it inside and out with the L2 ball, or with the L2 ball transformed by linear map. And sort of this mapping of thinking about our original body as just L2 only costs us square root d in the approximation. Okay, so now we can just apply this theorem of John with the data structure of Enigma-Tuani or Cauchy-Levy-Ostrowski-Rovani to say that for any norm space, we get a data structure with approximation square root d over epsilon. So square root d comes from the loss in this embedding, with space d times n to the 1 plus epsilon and query time d times n to the epsilon. Yeah.
Are you concerned about the pre-processing time as well?
Right, so it will be an issue, but not for this talk. So the pre-processing will be bad. Yeah. Good. Good. So right, so that we can already do for square root d. And the goal of these two works has really been to take a new approach to solve these A&N problems. And sort of at a very high level, the meta result is the following, is that we'll try to get upper bounds for A&N for a particular norm space x by studying the non-embeddability of expanders in x. So these are, I'll go more into details about what this means specifically, but the main application from studying it from this perspective will be the following theorem, which basically says that for any norm space and any epsilon, I'll design a data structure for x, which gets approximation 2 to square root log d, using space which is poly d times n to the 1 plus epsilon and query time poly d times n to the epsilon. So doing much better than what I would be able to do from John's theorem. Okay. Now, for this talk, I want to try to convey some of like the main ideas, and in order to do so, I'll talk about like random instances of this problem. So what this means is that if you give me a norm space X, the first thing I'll do is I'll discretize the whole norm space. So I'll think of like the points x1 through xm as some like fine net of all points within poly D. And then I'll define the graph, which basically takes all points and connects points if their distance is at most 1. Okay, so now I can define the A and N problem where the instances are randomly generated from this graph. So I can say that in my preprocessing phase, my data set will be a sample from the vertices of these graphs of n random points. And now my query will simply be a random neighbor of a random data set point. And now by definition of the graph, this will be a distance at most 1. Okay, so is the instances clear? It's like not a worst case instance, but this random instance of this problem. So we'll solve this, yeah.
And you can like reduce the whole problem to random instances like this, or it's just for intuition for us?
It's for intuition. There's a lot of work in actually solving the, like going from these random instances to the worst case instances. Mm-hmm. But yeah, we have a way to go. Basically, at a very high level, it's. Yeah, we do some sort of multiplicative weights update to try to guess the specific distribution that we're getting data set from in the queries. Okay. Yeah. Okay, so basically we just covered the first part of the talk. And now what I want to do is talk about sort of expanders and the cutting modulus, and then we'll talk about some geometric cuts in these spaces, and then going beyond John's ellipsoid. Okay, so are there any questions on the first part? Okay, good. So let's basically set up some notation. Let's assume that this graph G that I defined was some regular graph. So it's delta regular graph, and I'll define sort of the normalized Laplacian. It will be this matrix, the identity minus 1 over delta times the adjacency matrix. And so we can think about the spectrum of this matrix and sort of the smallest eigenvalue, which will always be 0, and it's realized by this all ones vector. And then the second smallest eigenvalue is lambda 2. This will be the smallest ratio of this quantity, which I'll call the Rayleigh quotient. Good, so this is just the definition. Okay. So now in the talk, when I talk about G being an epsilon expander, I'll simply mean that lambda 2 is at least epsilon squared. Okay. Okay, good. So let me first tell you about the sort of linear spectral gap inequality, and basically a way to relate lambda 2 to like these geometric quantities on this graph. So the inequality is the following. Basically, you give me any graph G, and now you give me a way to think of that graph as some points in RD, then I get the following. So I get that the average distance in L2 squared between the points is upper bounded by 1 over lambda 2 times the average edge distance squared between the points. Okay, so this is basically saying if you give me any graph, and you give me a way of thinking about the vertices of the graph as lying in some high-dimensional space. Now, if I measure distances in L2, then I get the following. So I can upper bound the ratio between edge distances and average distances. Okay. But let me give you like a, so that's some statement about L2. And now let me give you sort of a nice corollary of this inequality. If I think of the graph, and then I think of this embedding as being 1 Lipschitz, so now I think of my function that doesn't stretch too many edges. So this means that endpoints of a particular edge are at distance at most 1. Then I can say either two things happen. Either the points are contained within a small cluster, so a constant fraction of the points are really close to each other, or I get an upper bound on lambda 2. And this is like very simple corollary, where basically if we have f, which is 1 Lipschitz, then this right-hand side, this is always at most 1. And now if there's no cluster of points, this is telling me that most of my points are far away from each other. Okay, so I get a lower bound on this average distance squared. Okay, and this gives me an upper bound on lambda 2. Is that clear? But this is like a pretty nice statement. It's saying that you give me any graph and any way of thinking of the points of the graph as living in L2 squared in some in RD, then if I look, then either those points are contained within a small cluster, so either I can say these points are all close to each other, or actually the graph that you gave had lambda 2 being at most epsilon squared. from which I can apply Cheeger's inequality and get a cut of conductance at most epsilon in the cut. Okay? So now I'll give a definition that tries to sort of capture to what extent we can get this corollary for some general metric space. So to what extent does this corollary a property of L2? Or can we say something about general spaces? So it'll be very similar to what I just described. So the definition of the cutting modulus is quantity xi of a metric space X. This will be the smallest radius R, such that for any graph and any one Lipschitz map of the graph into my space, either there's a ball of radius R containing most of the points, or the original graph contains a cut of conductance at most epsilon. So just saying, take the corollary, and now see to what extent can you trade off the radius of the ball and the conductance of the cut. Yeah?
So, just to frame the discussion, I think we went through it, but so if X is L infinity, where does it... so the goal is to come up with a parameter that describes how well you can do for different
Yes,
known
exactly.
spaces?
Yeah. So we'll get a upper bound for L infinity as well.
And for L infinity, it matches
No.
what's
It-
known, or
So it matches what's known for this definition. But yeah, not, okay, so I'll relate the complexity of doing nearest neighbor search to this parameter. And this gives you a route to get an upper bound for L infinity. But if you take this route, it doesn't give the tight results for the
there it's known what's the tight.
Yeah, it's
some
yeah.
logs.
Yeah, so for if you're interested in just the problem of approximate nearest neighbor for L infinity, then yeah, you can do log d, and this approach will only give you log d. Yeah.
And related to what we think Marcus before, so are those algorithms are constructive in the end, or?
Yeah, everything will be an algorithm. Yeah. Okay. So right, let me give you maybe another way to think about this definition. So this definition is really telling me two things. It's like you give me any set of points, okay, and then either the points look like that, in which case I can say, look, there's a dense cluster of points within distance given by this cutting modulus, or if you give me points which are like roughly spread out, then what I'll do is I'll just define the graph where I connect points which are at distance at most 1. And what this definition is saying is that this graph must have a cut of conductance at most epsilon. Okay? Good, and the previous two slides, what we showed was that the cutting modulus of L2 was 1 over epsilon. Okay? Good. Okay, the main theorem of the first paper that we had was really showing how you can get upper bounds for the approximate nearest neighbor problem by getting bounds on this quantity of the cutting modulus. So the main theorem was that for any epsilon, there exists a cell probe data structure for A and N, which gives approximation order of the cutting modulus with space poly d times n to 1 plus epsilon, and memory probes poly d times n to the epsilon. So this will be in the cell probe model, so not yet time efficient. Okay. Are people aware of what the cell probe model is? Right, okay, so basically I'm not counting computation time, I'm just counting how many times you need to read from your memory. Okay, so it's like, once I read from memory, I can do arbitrary computation. So not yet time efficient. Good. Let me give you just like a flavor of how these things work. The idea is, okay, I gave you a metric space, I gave you a property of the metric space given by the cutting modulus. All you can do is just recursively apply this. So we'll partition our metric space using this cutting modulus, and this will build an LSH hash function for our underlying space. So the idea is like this. We start with our space, and now you'll build the tree by asking, okay, is there a dense ball? Okay, if there, let's say in this case there's no dense ball, then by definition we get a cut with conductance at most epsilon, and then we separate the points accordingly. And then we simply recurse on both sides. So again, we can just keep partitioning this graph G by asking whether there's a dense ball or not. Yeah.
So the smaller the cutting radius, the better you are?
Yeah, exactly. So, right. So yes. So the smaller the radius of the ball, the radius will correspond to the approximation that we can achieve. Right. Because okay. So what happens here? Imagine you get these points, and now there is a dense ball. Okay. So what I'll do is I'll just separate between the points that are very inside the ball and the points outside the ball. And now if whenever I fall inside the ball, then any point inside the ball is an approximation to my query. is basically the high-level intuition. But we'll simply recurse, and you can keep doing this to your graph until the underlying sets have measure at most like 1 over n. So if you do this correctly, you get like a depth of log n at most. But the data structure from this partition works like very simply. We'll sort of use the bucket as a corresponding hash function. So during the pre-processing, when you give me the data set, I'll simply look at my partition and traverse down this tree and put the corresponding data set points on the buckets which correspond to where that point lies. So basically, if it's a cut, I'll go to the side of the cut, and if it's a ball, I'll put in the ball. Okay? But now during the query, I'll do just the same thing with the query point, and then I'll look in the bucket, I'll check if there's any data set point inside the bucket. If there is, I'll compute the distance to that point. And if I find the near neighbor, I'll return it. Okay, so is the data structure clear from this partition? Yeah. But the analysis is like pretty simple. We'll just compute the probability that a particular point and its near neighbor are never split when we go down the tree. And this happens, so okay, each time we applied a cut, this had conductance at most epsilon, so roughly you split at most an epsilon fraction of the edges. And so the probability that we never split is at least n to the 1 into the minus epsilon. And now, because the sets had measure 1 over n, if you're doing this randomly, at the bottom, the number of data set points that lie inside each bucket is an expectation 1. Okay? So that's like a high-level intuition. This is for the random setting. Now, if this was for worst case, we'd simply repeat this n to the epsilon many times. Okay?
In the worst, but then you need, in the worst case, like, where you need randomness, I guess, to make your repetitions increase the probability.
Yeah, so
that comes in how?
So okay, good. So this was like for the random setting. When we're doing for the worst case setting, as I said, we'll get a distribution over these kinds of partitions.
Okay.
So we'll build this distribution, and we need to build it. We use use multiplicative weights to build a distribution like this.
Okay.
Yeah. Good. Okay. So I just gave you a data structure which works giving a bound on the cutting modulus, and the very nice thing is that very recently, so Assaf Naor, he proved that a similar inequality to what we had with L2, but substituting just a general norm x. So in particular, he proved that if you take any graph in any norm space, and you think of this graph as being points in that norm space, then the average distance between points squared in that particular norm space is upper bounded by this quantity times the average edge distance squared in that norm space. So it's like an analogous inequality where we switch, instead of L2, we're talking about general spaces, and now the value which you need to put in order to make this inequality true is not 1 over lambda 2, but log d over lambda 2 squared. Okay, so it's like an analogous thing, but similarly to the L2 case, we can get the same corollary in the sense that if we assume that this map was 1 Lipschitz, then we get that the cutting modulus is at most log d over epsilon squared. Yeah.
This is tight.
So I'm not sure if it's tight with respect to epsilon, but
With D, I mean the log D.
yeah, I think, yeah.
The log D squared.
Yes.
Yeah. Yeah. Okay, good. So, right, so using this with the data structure I just described, we get a cell-probe data structure for ANN over x, which gets approximation given by the cutting modulus, so log d over epsilon squared, using space d times n to the 1 plus epsilon, and memory probes d times n to the epsilon. Okay, so that was sort of the main result of the first paper. Okay, so now I'll sort of explain why there is a second paper, so why we couldn't go beyond cell probe and sort of what the problem was, and then how we'll address it. Okay, so I guess why was it cell probe? So let's just take a step back and review what we did. We defined this graph, which was some net of our space, and this graph had m points, which was e to the d log d many points. And now what we said is we were going to apply this recursive partitioning. So we were checking, okay, if there's a dense ball of radius log d, and if there wasn't, then we applied this inequality that Assaf proved to conclude an upper bound on lambda 2. Okay, so this means that the second smallest eigenvalue of the Laplacian is bounded by lambda 2, which means there exists an eigenvector for which I can apply Cheeger's inequality to cut. Okay, So if you know the proof of Cheeger's inequality, basically what this theorem is saying is that the cut is given by taking my eigenvector and at some point thresholding it and considering all the vertices for which the position of the eigenvector at that vertex is less than some threshold tau or greater. So that's what we get from Cheeger's inequality. But I claim that this is kind of a problem because doing this computationally will be a little hard in the sense that we define this graph and now we've forgotten about all the fact that this graph lies in RD. And we're just talking about this graph as a combinatorial object, and now we get some arbitrary cut given by the eigenvector to some matrix. So checking whether a point lied on one side of the cut or the other would require us to check whether this like v at the particular query was less than some threshold or not. And we don't know how to compute this eigenvector because it's just too large to store in memory. Okay, so we would need to sort of, in order to do this time efficiently, right, we need to use some more about just the fact that lambda 2 is bounded. Okay, so is that clear, or is there any questions here? So is the problem at least clear? We've taken a graph, you show that there exists some cut, but you have no bounds on how to determine whether a point lies on one side of the cut or the other side. Okay. This was sort of the starting point of the second paper. And the idea is that, okay, can we get all the guarantees that we got from the cutting modulus in a way which gives like efficient algorithms? So if you give me any norm space, and you give me a graph and an embedding of the graph which is one Lipschitz and a guarantee that there's no dense balls, now can I find a cut? But can I use the fact that this graph actually lies in my space to get a cut for which I can efficiently check whether a point lies on one side of the cut or the other? So let me give an example of what would be an efficient cut in this setting. So imagine maybe like the graph has points which lies in some space, and there exists some cut, but in addition, this cut is realized by taking a hyperplane of the space and considering all the points of the graph which lie on one side of the hyperplane or the other side. So this would be very efficient because checking whether a particular query point was on one side of the cut or on the other side, all we need to do is look at where that point lies in this d-dimensional space and check whether it belongs to one side of the hyperplane or to the other side. So this is an example of a very efficient cut. Another example would be maybe we could take cuts by taking balls. So you have this graph, and the sparse cut which you can achieve is actually given by considering a point in your space and considering all points within distance at most tau. So now again, checking whether a point was inside the cut or outside the cut simply corresponds to computing the distance of that particular point to the center of that ball. Okay? We won't be able to achieve that, but what we'll achieve is we'll come up with a function which will be efficiently computable, and now the cut is going to be realized by first applying this function to all the points in the graph and then taking a hyperplane. Okay? So checking whether a point Q belongs on one side of the cut or the other, we'll simply say, okay, take your point, and now apply this efficiently computable function f, and then check whether it lies on one side of the hyperplane or the other. So that's what we'll be able to achieve. This gives you an efficient way of determining at each point that you applied the cutting modulus whether your point belonged on one side or the other side of the cut, and this would give efficient algorithms for this partition that I described. Okay, so I claim that already with this inequality that I described, this like linear spectral gap and Cheeger's inequality, we can already get efficient cuts in the case of Euclidean space. So the lemma is that this bound on the cutting modulus that we had actually tells us that we can get cuts which are given by coordinate cuts, which means that if I look at a graph where I consider points which are close in L2, so points which are in L2 distance at most one connected, and this graph has, so if it has no dense balls, then there exists a coordinate such that if I take all the points in my graph for which that coordinate has value less than tau or greater than tau, then one such cut is actually going to be sparse. Okay, is that clear? I mean, yeah,
Wait, should that be obvious to us, or even just the statement?
No, it shouldn't be obvious, but that's just a statement. I'm saying that actually I can achieve these cuts by taking a coordinate cut.
Okay.
And so the proof was just the fact that Cheeger's inequality doesn't need the eigenvector. It just needs a vector with that minimizes the ratio between far and close pairs, or close and far pairs. So okay, good. So now for L2, in some sense, if you stare enough at this like spectral gap inequality and Cheeger's inequality, then you can already get efficient cuts. And the goal was to somehow reduce any norm into L2. So the task would be to get an efficiently computable function that I can control the average distance in L2 squared after applying this function, and the average distance in L2 squared of an average edge. Okay? Now, John's theorem would do the trick here, but we would be losing a square root d factor. And in particular, John's theorem actually tells me something much stronger. John's theorem would say that everything inside the expectation is preserved. All distances are preserved to square root d. All I care about is the ratio between these quantities, this like average notion. Okay, so let me show you just how this is done for LP spaces. So I'm going to get nice geometric cuts for spaces in LP where p is greater than 2. Okay, the lemma is that you can get coordinate cuts for LP spaces, and this was shown by Matusik. It says the following. So you have a graph G, and you have an embedding of that graph into LP, which is 1 Lipschitz. Then either the points are contained within an LP ball of radius p over epsilon, like constant fraction of these points, or there exists a coordinate such that, and a threshold such that the cut given by considering all the points with coordinate k being less than this particular threshold has conductance at most epsilon. So we can get the bound of cutting modulus of p over epsilon, and in particular the cuts that we're getting in this partition are given by coordinate cuts. So the same, yeah. So in other words, this is what we get. Okay. Now let me define the transformation that will take from LP space into L2, and that will allow us to control this expected edge distance and average distance. Okay, so this is the sort of, it's known as the Nasser map, and the transformation is very simple. We'll simply work in a coordinate-wise way, and we'll take each coordinate and multiply it times the sign of that coordinate raised to xi to the p over 2. Okay, if you think about this map, basically for any point, the LP distance to the p is the same as the L2 distance squared after applying this map. So just by expanding literally, it's just algebra. And now a nice property about this map also satisfies that for any 2 points, then the distance in L2 squared of after applying these points is upper bounded by p times the original distance where we scale. And if you think about what's happening in like 1 dimensions, then this is taking like a linear approximation of this function. So if you take the derivative and you see what's happening, then you'll get a bound. You're saying basically the points can't separate too much. Good. So right. So now we need to prove this. We need to bound this ratio of average edge distance to average distance. And we'll basically take a graph and think of this function as being 1 Lipschitz. Now, if there's no ball of radius p over epsilon, this means that when we consider applying the graph, so applying the Nasser map, now we get the following guarantee. Because the L2 distance squared, this roughly will be p over epsilon to the p, just because this L2 distance squared would correspond to the LP distance raised to the p power in the LP space. And since we assumed that there was no balls of radius p over epsilon, then we get the following lower bound. Like there's some caveats here. It's like up to translation of the points. Yeah. But okay, so we get a lower bound on this quantity. And roughly by applying the fact that the edge distance were at most 1, then you can apply the upper bound on the Nasser map. And at a very high level, you can bound it by this p, this is the value that we lost from the Nasser map, times the average distance to the p over 2. This is because we were losing as our vectors got larger. This Nasser map has a worse guarantee. But basically, this gives us a bound on the ratio in L2 distance squared, which is 1 over epsilon, and this is exactly what Cheeger's inequality needs in order to cut. Okay, so after applying this Nasser map, then we can work in L2 and get a coordinate cut in there. Okay. Okay. Are there any questions? Okay. Okay. So simply applying this with the data structure for the cutting modulus, we get that for any epsilon greater than 0, we can do the whole data structure with the cutting modulus in a way that's an efficient manner, and get approximation p over epsilon for LP spaces. Okay, this is what we showed. Okay, so let me go to sort of the final part of the talk, and in which case I'll try to do the same thing that I did for LP spaces in a more general way. Okay.
Did you say how you find the coordinate that has this cut?
Right, so this is done during pre-processing, so in some sense you could go through all of them. Yeah. Yeah, so this is actually generating the partition is all done during pre-processing, and we don't count the computation time. But once we have the partition, you know it's given by a cut, so you can efficiently store it and like very quickly check whether a point lies on one side of the cut. Good. Okay, so let me go on to the last section unless there's any questions. So I have a lot of time, so I went a little fast. Okay, so let's try to sort of go beyond John's theorem, and I'll just remind you what John's theorem said. Is that basically for any norm space up to factor square root d, we can think about it as being L2. Okay, so John's theorem actually gives us a bound on the cutting modulus with efficient cuts. You basically take your points, you map them with John's theorem, but it loses this factor square root d, so we're back at the embeddings approach. So we don't want to do this. And what we want to do is find the map, which is sort of analogous to the Nasser map, that works for any norm mapping x into L2. Okay, and that's what we'll actually show. Yeah. So let me give a construction of Daher from 93, and this will be basically trying to do the analogous thing that we did for LP spaces for these general spaces. So first I'll give you a picture of what's going to happen. So the picture is the following. We'll start with some arbitrary norm here, and we want to get to L2 here. So what we'll do is we'll just perturb our arbitrary norm by a little bit, by some like sub-polynomial factor, and also perturb the L2 ball. And now from these two balls, we'll get like a map which works like the Nasser map. It's not quite, so it'll be like 1 over square root log d holder. So you get some continuity guarantees, but not as strong as the Nasser map. It depends on square root log of dimension. Okay, so that's the picture of what's happening. I'll just give you the statement. It's basically saying for any norm space, there exist norms A and B. These will be a perturbation of x and of L2, such that A is like close to x, B is close to L2, and now between the unit sphere of A and B, there exists a map for which I can upper bound and lower bound in some sense, the distortion. Okay, so that's just the construction of the picture that I had before. And this you should compare to John's theorem, which just says that I can just go straight from my original space into L2, and I get a map which is Lipschitz, but the Lipschitz constant is square root d. Okay, so in some sense the comparison. So these are like the two pictures again. That's in some sense what to have in mind. But now we can, so good. So now we can do the same thing that we did for L2 by using this map of Daher rather than the Nasser map. And basically we can say that for any norm space and any graph, once we have one Lipschitz map, then we get the guarantee that either there's no dense balls of radius 2 over epsilon to square root log d, or after applying this map, we can look at the points, and those points have a coordinate cut of conductance at most epsilon. So it's the analogous statements for LP, but for general norm, after applying this map of Daher. Okay, good. So the construction is based on this notion of complex interpolation, and actually we show that you can actually compute this map efficiently. But the proof is really analogous to the LP case. So I'll conclude with some open problems. And some problems that are specific to ANN is to try to compute this cutting modulus for spaces that we actually care about. So for instance, for the edit distance or for the earth mover's distance, can you give some like good upper bounds for the cutting modulus, which will correspond to good upper bounds on the nearest neighbor? Okay, so maybe another idea would be to define this this cutting modulus with respect to vertex expansion. So this bound was giving me cuts with conductance at most epsilon. Maybe I can consider the cutting modulus which trades off the radius of the ball with cuts of vertex expansion given by some bound, and there's some indication that this could actually give better bounds. So basically the question that Mark had about getting log d for L infinity, basically, so the algorithm, Piotr's algorithm of that actually gets this log d can be interpreted in sort of this way. Another question would be to actually do this with efficient preprocessing. So as I said, our preprocessing is we don't have a good way of like finding these cuts or doing this partition. So that's another very interesting thing. And maybe more broadly, it would be nice to try to get these geometric cuts that maybe actually achieve log d. So maybe like in the cell probe model, we can actually rule out when we have no clusters of radius log d, we can get a cut of conductance at most epsilon. Now, when we went through this approach, we were losing like 2 to square root log d, but this is just a matter of the fact that we took this approach. Maybe there's better ways to bound this. Or maybe just getting simpler cuts. I mean, our cuts are like pretty complicated in the sense that you first need to apply this function, which is computing like complex interpolation. It's like very complicated. Maybe there just exists cuts that are realized by balls or something, like some simpler geometric objects that could actually realize these cuts. And another application would be nice to apply sort of these ideas to more generally to other problems. So basically the main point is that John's theorem is giving you something like very strong guarantee where you can actually preserve every pairwise distances. And sometimes we care about just average distances. And in fact, sometimes you can do better with these settings. But yeah, that's the whole talk. So thanks.